think more for you. So please equip yourself with one Linux, which is workable, like 2. What is it? This is Ubuntu 14 point something. Okay, whatever version you have, because I want to try something with you together. Okay, and make sure you are connected to power when you try this, because it may drain many power. Okay, so what is that? It is hidden inside here, the GitHub page, and the elite class folder. There is a subfolder called, let me make it bigger, subfolder called scheduler control. Okay, so we've got 3 programs, and this is the basics when you are trying to understand what the scheduler can serve you. Okay, so what are they? They are this. Okay, the thing that I talk about in the lecture, right? You still remember in the lecture that I just spent 5 minutes, okay, to talk about the Linux scheduler. Now, basically, the Linux scheduler classifies process into 2 classes. Okay, so we have the real-time process, which are those only be able to be set up, only be able to be launched by the administrator. And for others, the normal processes are the process that you launch. Okay, so I think you want to try how to launch a root-only type of process. So I give you some warning. First of all, your VMs, okay, if you want to experience what will happen, make sure that your VM has only 1 core. Okay, so how can you check? You can go to your, I'm running this, setting, and the system processor, I have 1 core only, okay, 1 CPU, 1 core, okay. Make sure that you get 1 CPU, okay. If you do have 2 CPU enabled, don't worry, it just makes your experience not so outrageous, okay. So what's the outrageous experience that I want you to go through is, okay, I want to set up a real-time process, okay. So what is a real-time process? So a real-time process is actually a process that's always favored by the scheduler. The scheduler always chooses this guy if it is going to be real-time. And when you launch a real-time, that means that you will beat all your local normal process, including your login interface, including your terminal. So when such a loop, let's say you have a loop for 1 million times, will take the entire CPU attention. Your system will get frozen for that moment. Okay, then will suddenly unfreeze. Okay, then the real-time process, okay, we have some numbers, okay, you've got some range here. It's basically tell you one thing. You can download our code here, and you will find 3 programs. I want to launch the first program with you, okay. So it's the this is a safe process, okay. This is not something horrible, okay. It just QE the system, okay, and you can take a look at the code later. It just QE the system. What are the level of the real-time level? We call it the real-time level, real-time scheduling level, or in a class we call it static priority. So what is a static priority? We can have static priority from 1 to 99. Okay. So if you want to take a look at the code, it's very simple. It's basically ask the system, hey, what is the minimum priority for sketch other? What is the maximum priority for sketch other? And I just QE for 3 times for different scheduler class. Okay? So what is the next thing I want to show you? The next thing I want to show you is the program called, sorry, I skip the code. It's called simple set schedule. Okay, I just want to set the scheduler policy. So what is the setting here? So I just have some checking. Oh, by the way, how many of you know this call? String to long. How many of you know it? No one know it? And you don't even know what is that? The string to long. Okay. Then what is the difference between this guy and A to L or A to I?
I remember this is safer, but I forgot the reason.
Yes, this is safer. Okay, so that's why I prefer this over A to I. Okay, I seldom use A to I because let me ask you a question. What if I put ABC in a string, in a string and type A to I, put a string inside, ABC, so it should give you error. 0. It means 0 is an error. But what if the number that I have is 0? Then what is the meaning of error, right? So this string to long will check error. Okay, so I put down some code here. This is my preference. Okay, you can forget about it. Then I do something. So first of all, this is a requirement. I have to use a sched get parameter to get the parameter of that PID. Okay, so let's say I launch a loop. Okay, I launch a loop program. Then I query the PID of that loop program. I put it here to get its parameter. Then after I get the parameter, I will change its parameter, set its real-time scheduling level to 99, the highest possible level. Okay? Set it and also change its scheduling policy to F50. Then what will happen? Very interesting. Okay? So let me open one more terminal. Okay? So this terminal, you don't need to see what is going on. I just use it to launch an infinite loop program. I already provide an infinite loop program. The infinite loop program, you can control. I just type something to let you see it. Okay, so you can choose a looping level 1, 2, 3. 1 is very fast, 2 is slow, 3 is very slow. Okay, so make sure that you don't choose 3. Okay, you choose 3, you need to reboot your computer. Okay, then I will choose. Let's say, let me try 1. Okay, 1. So very fast. Done. So that's interesting, right? 2 approximately takes some time. Okay, take around 20 minutes, 30 seconds in my computer. Okay, so I just Control-C it. What I'm doing is you need to launch this program as a root. Okay, as a root. Then don't worry, it will ask you for a PID. Okay, so what I'm doing is I want to launch this loop program for 1 to 2 seconds so that I can get the chance to this terminal and set this looping program to scheduling level 99 and see what will happen. Okay, so let me start the program here. So the program I start is 2291. Okay. Now let's see what will happen. 2291. Enter. Then my computer is totally frozen. Yeah. Oh, come on! Oh, come back, baby! Oh. Yeah, nothing. Again. Okay. See, I said it's dangerous, huh? Okay. Again. 2295. 2295. Okay. Enter. Yeah. You guys cannot see it. What? Back sucks. Okay. Coming. Okay. So it's just stuck. Let me do it again, Do it again. 2298. Okay. 2298. Enter. Entire system frozen. And I cannot type anything. Yeah, and suddenly say that from now on it will seize the CPU, and this guy really finish in a very quick style. Okay, because this loop program will take the entire CPU. You can try. And as a matter of fact, the new kernel has implemented something like we call it a real-time throttling. So what's real-time throttling? Is if we find that some real-time process really jam the entire system, okay, then it will throttle. Throttle means lower is running priority, so that this guy won't take the CPU, okay. So you can try later, okay, because I know that not everybody can put up the computer, not everybody download my code, okay. So this is a very interesting demonstration, and you can submit it into different levels. You can submit it into RR, just change my program. Then you can submit it in the ch under RR, and then it will go in a round-robin way, okay? And I already explained to you in the class that what will happen if I have let's say the 99 class submit with F50 and RR. in a class, regular class, I go through it very fast, okay? Now you can see what will happen. Let's say I have an FIFO first, then it will go to the CPU, execute until it dies. Then you will have the next RR comes in, and RR already have some quantum there, let's say the non-zero. Then it will spend some time on CPU, then we'll let the another RR to go. And what if we have another FIFO comes in? We will let the FIFO to continue to run until the end. Okay? So today we will take a look at the scheduler, how scheduler implement this. Okay? Scheduler has a very interesting way to implement it. Okay? And if you want to know more, you can take a look at the main page of this 1, 2, 3, 4, 5 guys. I all call this 5 guys in my demonstration just now. You can try later. Don't get frustrated that I cannot try it. Okay. If you want the effect that I have, okay, I can come to your machine and fire an infinite loop. Okay. Then you need to reboot your computer. All right. So what is the scheduler that we are taking in our focus? Our focus is the out of date scheduler. Big of N scheduler in Red Hat 9. So everybody, how many people get the Red Hat 9 ISO and install it? It's just 1, 2, only 2. Okay. So later on we'll do it together. This guy is a big of N. This doesn't mean that it is a slow computer, right? It's used to be a server that's serving you maybe at your child age. Okay. Then you visit some site. It's already running it. It doesn't mean slow. It means only that when it's trying to look for a scheduler, look for the process to run, it takes big O of N time. In the worst case, okay. In the best case, it's big O of 1. Just pick the next guy. Hey, come on, okay. Then later on, we will highlight which part of the scheduler take big O of N time, okay. So everybody know big O of N. If you don't know big O of N, okay, I will give you some form, okay. Yeah, from this course, of course. Okay, and we have some structure. The structure is called 1Q head. When you see a head in the kernel, you should immediately map it to something. What is that? The last time we talked about the linked list, right? It's actually the linked list. Usually with the head, that means that it is the linked list structure, the linked list head, and the circular linked list structure because it's just a node. Okay. So whenever I find this is the list, and we use a run queue head to organize all runnable process. Another 2 head, okay, in this example, is to manage a particular device. Let's say there is a process waiting for CD-ROM or another process waiting for keyboard. They will join its own wait queue. The device has its own wait queue, and join this so that it won't go into this queue, and the scheduler won't choose this guy. So this is what is the mechanism that I always said in the class, saying that that guy waiting for something, it won't be selected. It's because of this. It just pull off that queue and join another queue. Okay, and these 2 queues won't go to the scheduler. Only this queue go to the scheduler. Okay. Then we have some, first of all, some what we call vocabularies. So what are the vocabularies here? The vocabularies here are all concerned with this file. So where can you find this file? Let's go together. We launch a browser. Yeah, forget about this 燃燒肝臟. Okay. So let's go to the LXR free electrons. Okay. So I'll wait for you guys. So we'll read the source code together. Okay. So this guy. We go for the old kernel. So what is the old kernel? The old kernel is 2.4. Let me make it bigger. 2.4.37. Okay, so this is our target version. Let me make it wider. And later on, we will install this new kernel in a Red Hat. Now, inside this, we will go to include. Go to include. And then Linux. Include Linux. Hey, come on. All right. Then what is the file that we look for? We look for the sched.h. Scheduler.h. Okay. So start with S. sched.h, where you okay, is ch, oh yeah, this one, okay, so this one, sketch.h. So I will stop it here, wait for you guys. So the path is include Linux sketch.h. If you cannot remember it, yeah, the path is here, include Linux sketch.h. Okay, so we will go in. So here is a very, very important thing here. It contains the structure for holding the entire process. So what is the structure name? The structure name is called, I don't have a link here. Oh, sorry, I forgot to put, here, task struct, okay? The structure name is called task struct. So let's look for the definition. So Control F and task struct. Okay, so we have 40. Okay, 40 matching locations. So I put down something more bracket here. Okay, so I use this keyword to look for it. Okay, struct, task struct, and then open the curly braces. Then you will find the definition of the task struct. Okay, yeah, a huge structure. That structure represents one process in kernel. Okay, so can you guess what is the first field? State. What is the first field? Can you guess it? Can you guess? It's the state of the process. Whether it is block, running, vulnerable, it's not vulnerable or unvulnerable, or other status, it will state that this process is vulnerable, or even exit is become a zombie. It's all inside in this stage variable. Okay? So for some others, like whether you have any signal pending, you receive some signal. So in the class, I say that, oh, when you die, you will send a sick child to the parent, and at that moment, this sick pending field will get turned on. Okay, so it's all hidden. Now let's go to some real important stuff. Okay, this field guys are very important. Okay, but you know, I already tell you that in the kernel code there are not too many comments. Okay, so what is the counter? When you look at the counter, counter means a count from 1 to 2 to 3 to 4. Okay, so in kernel it's do reverse. It's the countdown counter. It is the quantum. The counter is the quantum. The nice value, yeah, how nice you are. How nice you are. Okay. Some others, what are the processor you are working on? Basically, I can give you a summary here. We also have a PID. What is a policy? So you can find a policy field. Okay, you will find a policy field filling either one of the possibilities here. The quantum using the same units as the jiffys. Okay, the jiffys that we tried some time ago. The static priority, the dynamic priority, the process status. Okay, so it's all hidden inside here. Why I give you these fields? Because later on you will see the scheduler will follow these fields to work and to select a process. Okay, and what is a scheduler? The scheduler basically works like this. Okay, whenever the scheduler get a request saying that, okay, I need to schedule someone. Okay, so what they're doing, first of all, it will go through a selection loop. Okay, and the selection loop, okay, will count every process to find how good a process is. So there is a very ugly named function called goodness. Goodness. How just like Hong Kong a famous magic word, goodness. Goodness, okay, goodness and goodness. So this is how good that process is, and we will find the best process or not goodness. Okay, the best process to run within this big of n loop, and after this big of n loop, we may have a chance that we cannot find anyone. Okay, why? Because all processes has used up their quantum. So there is another big of n loop to recharge every process. Okay. And after we charge every process, okay, I say, oh my God here, because the kernel needs to run something very quickly. So they will go back to the selection loop using goto. Okay, so it will use goto to go back. Okay, and after this go back, it will finally find someone, because now all people get quantum, so you will find how good a particular process is. Last, we will go to context switching. Okay, so this is the basic design of the big of n scheduler. And we will start reading from this line. So what is this line? Let's click on it. Okay, so this is again a free electron page. Okay, so the 547 line is the start of the scheduler. The scheduler code start here. Okay, so you will find something that you don't understand. Okay, some of it even I don't understand even now. Okay, some of this kernel lock we know this is the what we call a big kernel lock. Okay, so you can skip something, skip. If you find something you don't understand, you can skip it. Okay, this is the mentality to read a kernel code. Okay, you don't understand. Okay, skip. You don't understand, skip. And then you finish the whole function, you get nothing. Okay, yeah, then don't worry. Okay, so this is something that you know, you understand now. Okay, there is a keyword here called unlikely. So does anybody know what unlikely means? Anybody have heard of? Yeah, this is a normal GCC. Whether GCC or CLAN, I don't know, but GCC must be able to understand. It's not a function, it's for GCC to look at. Okay? So if you are later on take a course called, who are CE people here? Sorry. I feel sorry for CE program. Okay? CE people will take a course called v2.4. Okay? Do you know what is v2.4? Computer architecture. Okay? So the computer architecture course will teach how to design a CPU. Okay, so CPU, the normal design of CPU is that, oh, you give me an instruction and I execute. But nowadays, CPU will do something we call branch prediction. So what is a branch prediction? Whenever you find an if-then-else statement, okay, there should be some branch has a higher priority than another branch. So it will predict it and pre-compute that branch for you. Unlikely that you will give up that branch, then it will just like, oh, we waste all the previous computation. Okay, no problem. We just do it. Okay, do it. Follow your order. And this call unlikely is to tell the CPU whether you should do branch prediction or not. Okay, so this means that it is very unlikely. Don't predict it will happen. Don't pre-compute that branch. You should pre-compute its else branch. So happen that we don't have else branch. Right? There's only if, no else. Okay? So that means that there is a reverse. The reverse is likely. It's likely and unlikely. Okay? And if you're interested, it will cause branch prediction, pipelining. These are the keywords. Okay? Of course, you are welcome to sit in the CENG v4.20. Okay? I hope that professor should teach about the pipeline and branch prediction. Okay? And this is for GCC to know it. So that's why in a normal code execution, this doesn't mean anything. You just cover your eye and say that I don't know what it is. Okay? So some keywords here. Also one more keywords, the previous. So what is the previous here? Let's go back a little bit. Okay, go back a little bit here. This line 559. So what is current? Current is a magic keyword in the entire kernel. Entire kernel, whenever you see the keyword current, it means the process that is currently executing. So it means something strange, right? I am in the scheduler. What is the meaning of something executing? So that means that if, let's say I have a process running and you interrupt it, then before the interrupt, that guy is the current. Okay, so the current means that you can, just blind your eye and say that, oh, this is the executing process. But to be precise, this is before the interrupt. It is the guy who is running on the CPU. So we call it current. And now the scheduler say that, okay, I want you to use another guy to become a current. So just back it up to be the previous. So that means this guy may leave the CPU, and why it leave the CPU? Maybe because of this. What is it? What does it mean? It means the previous guy, the scheduling policy is a round robin policy. Okay? round robin policy, and that's means that your time is up. Okay, your time is up. That's why you go to the scheduler. And when the time is up, what should you do? You should also double check it. Double check what? What is the statement? Double check whether you have used up your quantum. So counter is a quantum. So if you use up the quantum, then it do something else and you don't understand it's no problem. Later on we will come back to this statement and we will have the move last run queue. So to move the current process to the last of the RR queue. So this is the thing that we implement the RR scheduling policy. Okay, so quite easy, huh? But if I ask you to stand here to say that, you will say, this is this, and we can't zero, done. Okay, right? And you, because you don't understand, right? And yeah, so other status we will try to avoid it. Okay, we will go to the core stuff. The core stuff is here. The core stuff is here. Okay. So what is the stuff here? You will find the corresponding illustration here. So it's about the goodness function, okay? And before we reach the goodness functions, there is a loop. Can you find there is a loop here? Still remember last time we talked about the linked list? List for each. Okay? The list for each. So this is the kernel list.h, right? So this is the loop, okay? And can you guess what this loop is doing? It's used the list entry call. What's the list entry call? It's actually the container of. It's a container of. So you go through the linked list and queue up that guy, and that linked list is the run queue head. So that means all of the processes that in the queue, and the structure is task struct. Okay. So this loop is to go through every process. This P, what is the P? Let me go back a little bit. So the P is here. It's the task struct. Okay. So we go through the task struct one by one. So this is the here is the point that we have the big of n performance. So you have many processes, so the loop will take some more time. Okay, and you cannot find any break here, so that's why you will scan through the entire queue. Okay, you won't stop. Okay, and the point is that you will go through this what is called the goodness function every time. So what is the goodness functions? So let me give you some high-level point of view. The goodness function is to calculate a score for a process. If the score is high, that means that this guy is better to be scheduled. Okay, so let's take a look at what is the policy in a scheduler. The scheduler first check with some measurement. You don't need to remember whether it's -1 or -1000. Okay, we focus as a schedule order first. If the process is a schedule order process, that means a normal process, then it will update the weight with the quantum remaining value. So why there is a remaining value there? Because maybe there are some process just recharge and never get a chance to get in the CPU, so it will get a non-zero counter, or you got interrupted by another process, then you still have some counter left. And what is the next? Next is how nice you are. Okay, the nicer you are, then what is this value here? The nicer you are, the higher score, lower score? The lower score. So don't be a nice guy. Okay. The nicer you are, the lower score you have. Okay. And some of the scheduler policy, if you're in the same CPU, give you some bonus. If you are using a same piece of cache, give you some bonus. And that's all. That's all. Very easy to calculate the score. So what is the priority? The priority is if you get quantum left, schedule you. We want to schedule you. If you are not a nice guy, okay, a bad guy, I will schedule you. Okay? So usually all processes won't change the nice value. Then that means that if we think of it as a very simple system, never change the nice value, then it will finally follow two things. What is the two things? The first, whether you get quantum flat, and one more, Q position. Why it is about the Q position? Let's take a look at this code. Okay, so this code, after go through the goodness function, okay, this line you should know what it is, right? I teach that it's ENGG1110. Huh? What is that? Don't tell me you don't know. Huh? Oh, which line? Oh, this two, together with the whole loop. It should be understandable. You need to discuss. What is that? What is that? What is that for? What is that for? Oh, I'm stunned. Oh, by the way, you don't need to care about that comma. I even don't know why it's a comma. Okay? Does it because it wants to save two curly braces? I don't know. Don't ask me why there's a comma. I think it's really for saving the curly braces. But you don't know what is comma. Comma means that you can have more statement behind it. Okay, so these two together is a statement, and the return value is this guy of that statement. Okay, so it's actually equal to C equal to weight semicolon, and then next equal to P semicolon. So that's why I say that the purpose of it is to save the curly braces. Yeah, you don't get it. Okay. So what is this loop is for? Easy, find the maximum value, right? And why I say that it's not just depend on the counter. Why it is depend on the Q position? The position of that process in Q makes a big difference. Is it? Yeah, some say yes. Here, say yes or say no about this fact. The process location in the queue make a difference. Yes or no? Don't get it? What happens if this is way bigger than or equal to C? If we change it. Now here is, whenever you encounter, let's say all processes get the same quantum, all processes get the same, what is my rule? Same quantum, same nice value, even same CPU, same memory cache, then they will get the same results, right? Then, who do the type breaking is the position of that process in queue. The more close to the head you are, the more you get be able to be selected, right? It's because of this control. So it is a hidden RR, right? This is actually an RR scheduler, hidden, okay? With the control to change something, let's say that we favor, just not a pure RR, but I favor someone who get a lower nice value, I favor someone get a higher remaining quantum value, so on and so forth. Okay, so if that's the case, then you will get a sense that what happens if I have a fork system call, and the fork system call is enqueue a process to the end of this scheduler queue. Then you will have always the parent to run first, not the child. Yeah, of course you can change just one line. Let's say, oh, we are not inserting at the end of the queue, but insert it at the front of the queue. Then it changes the story. Okay. So that's why I said this course is to disclose to the code and you know the truth, okay? 有code有真相. And then what? And then after this loop, we will finally find someone who has the highest score. Of course, we will have something that we have some buggy scenario is that we have a set of CPU that is not able to be scheduled. Let's say this get a zero quantum. I cannot schedule it, okay? Then we will have a very unlikely scenario, unlikely, that C is 0. Okay, so why C is 0? You say that, oh, C should be a minus 1000. So this is the chance that we have to go into this goodness. The goodness is in the same file. So you can go further up, further up, further up. Yeah, maybe I search goodness. Goodness. Oh, here is goodness. Okay, so see, we have comments now. Whenever you have a comment, this is big stuff, huh? Process the value goodness, the larger the better. Real-time process always get 1000 goodness value. Out of time, that means we try to reschedule. We charge all quantum, then we will return 0. So you will see that the loop is like this, right? You will have a policy where there is others, then the weights start counting. So what if we have a counter equal to 0? So you will set the weight equal to 0. Okay, and eventually you have a chance that's to return the weight here. Okay, if you're interested, what is this? Okay, do you know what is this actually? No one seen this before. Okay. Yeah, this is the tag for go to. Okay, so let's say that you go in here, and then you suddenly see this line. Okay, it is an unconditional jump. When you see this, jump to here, return. Yeah, this is go to. Nice. I love using go to with a controllable way. Okay, don't write down go to. Let me put some tags and random go tos here. Then you just, I don't think you can trace the program. Okay, and one more thing. Go to is only valid within the same function. You cannot say that from one function go to another function. Okay, go to only within the same function. Okay, so you use go to, but you know what I mean. For me, is yes.
Why not directly return?
There is one coding style that upheld by the kernel group. Okay, they hate to have multiple return. Okay, and one more stuff. Usually they do this. Of course, this doesn't appear. Before the return, they will have some clean house stuff, like the LK memory, so they can group all the clean house thing together. Okay, using the go to. Okay, so this is a go to statement. And the go to statement, why it will return 0 is because you keep on selecting stuff, processes that cannot be scheduled because of the counter equal to 0. Okay, so whenever that happens, unlikely this line, okay, then we will have to recalculate everything. Okay, so the thing is very interesting. Okay, so it will go through a for each test loop. Okay, so it says to loop through the process queue, and the counter is equal to remaining counter divided by 2. Do you know that this means divided by 2? Shift bit divide by 2. Okay, we don't call divide by 2 too slow. Okay, shift bit. Okay, divide by 4, shift 2 bit. Okay, multiply by 2, shift to another side 1 bit. Okay, so it is much faster. Then it goes through some nice value conversion into context. This is the macro to convert it, and this macro is amazing, really amazing. I should use the Steve Jobs words. Amazing. This is okay. So what is this amazing call? So this is the part of the nice to take definition. Take a look for a while. I give you 1 minute and answer me. Okay. And first of all, let me tell you what is HSET. HSET is a category of the CPU. If you are over, this is not exactly the Hertz number. It's a categorization. If you're using a slow CPU, you will get a slow HSET. If you're using fast CPU, you will have a big HSET value. Okay? Tell me, what is the kick scale called? The kick scale called is this guy. Kick scale is equal to 20 minus nice value, and go through this transformation and give you this value. I give you 2 minutes. You tell me, if I have a fast CPU, I recharge, because this is the recharge call, okay, the recharge call. Whether I recharge with a higher value or smaller value, if I have a fast CPU. If I have a slow CPU, whether I get more quantum or fewer quantum. So this is a quantum. Why is this quantum if you cannot get it? Here is a statement to recharge the quantum. Okay? Take a look. I give you 2 minutes. Very amazing design. Already finished? Okay? Fast CPU, you get a large value or a small value? Was this something? Steven, start. Large. Slow CPU? Small. Okay, then you get the correct answer. But why is that? Can you guess why is that?
Because a faster CPU can execute faster. So so if you recharge it in a larger clock value, you can still execute it very fast.
So that means, let's say the time is like this, okay? You have more quantums, so you can go up to this level, let's say. If you have more, then you go up to the level. Now let's do it in a reverse way. Why the slow CPU gets fewer?
Because it takes time to execute so many operations, so it cannot recharge too much. Otherwise, each task will execute for too long.
Very good, very close. I mean, we can summarize it just one sentence. Okay, the sentence is: give different classes of CPU for each process the same amount of real time to execute. Okay, so understand this. This means if you have very good answer, thank you, Stephen. The conversion is you got a high speed CPU. I give you more quantum. Let's say that amount of quantum stuck up with 1 millisecond. Let's say 1 millisecond. For that 1 millisecond, if you put it back to the slow CPU, you should not give them so many context or so many chance to execute using a big quantum value. You should put fewer quantum value so that it will share a smaller context, and so happen it just also fits in 1 millisecond. So this is a very elegant design to give you the same experience. You have a slow CPU, you won't feel your system very slow. Yeah, because I mean I shouldn't say this, but yeah, it seems that I buy a slow CPU, then I can do the. You can do a something. Let's say a browser and also a video player. Okay, you won't find too laggy because now they will have a kind of a similar time on the CPU. Of course, they cannot finish the job with a shorter time, but you will have the same feeling that every job will get in the CPU for a specific amount of time, and it's close to the case for the fast CPU. Okay, it is a very elegant design. And also look at one more case. I just want you to look at the magnitude. Now look at here. What is the properties when you focus at the nice value? If you are a nice guy, you will be charged for more quantum or fewer quantum. Nice guy means you have a big nice value. This part. If you're a nice guy, you have a smaller value. If you're not so nice, you're a bad guy, you have a bigger value. So the nice is very interesting. We can just generically call it dynamic priority. It's not just priority. it will affect the amount that you get every time you get recharge, and also it will lower the chance that CPU chooses you. Yeah, so don't be nice. Okay, you will get fewer share of the CPU and also less chance to get in the CPU, and you are always the last guy, maybe last guy to get in the CPU. Okay, so nice is not really nice to you. Okay, then we go back to the code. Now you understand that, okay, we have two loops. One loop is to calculate the goodness. The goodness itself is just a big if then else. And after the goodness, we will have an unlikely scenario that no process can be chosen. Then we will go through a selection of, well, not selection, a recharge loop using the if each task, okay? And after that, it will use the go to statement to go back to somewhere. Where is it? Let's see, it's called repeat schedule. Copy, paste. See? The go to statement, you finish, recharge everything, boom, go back to the selection again. Okay? So, really nice, try it in your later assignment, or I don't know what kind of assignment, Yeah, just try, but don't submit it, or your tutor say that, oh, what is your program? I cannot trace, okay? Then we will go to other stuff, okay? The other stuff is not quite interesting, okay? So they are doing the context switching accounting and prepare the switching and so on and so forth, okay? So before we have a break, okay, we will go to take a look at one very important checkpoint, the call we call switch to. The switch to call is the real stuff that will take place in a CPU in order to switch from one process to another. And by the design of this call, actually what it's doing, I've got animation here, okay? The theme-based animation. The theme-based animation do the following. Let's say, currently we have a process I don't know why, maybe you get an interrupt or your quantum has just up. Then you will go into the schedule function, the scheduler. The scheduler go through the big of n steps to look for which process to be selected next. Let's say the next process is J. Let's say the next process is J. Then after we find it, we will choose the function called switch to switch to process J. And the moment that we finish calling switch to, by magic, we resume the execution of process J within the scheduler code. What is this about? What is it about? Very interesting observation, okay? And let me tell you the story. The story is like that. Actually, all process, when let's say there's a 1, 2, 3, 4, 5, up to n process now, okay? They all executing and suddenly got interrupt or use up quantum. Then the next step is they go to in the scheduler. The scheduler won't choose it and choose another guy. So the moment that they find that they have to give up the CPU, actually they are still executing scheduler code. They are still executing scheduler code. And you switch to another process, okay? And that's why you will find many processes running up to this moment and waiting for another guy to rescue me. What is the other guy to rescue me? Another guy also go into the scheduler and find that, okay, it's time to choose, let's say, choose number 3 process, okay? And what is the control here? Maybe the control is a time interrupt. Now, this is a very complex function I don't want to trace with you. So the high-level point of view is that every time you get a time interrupt, the time interrupt handler will do one thing. It will update the process time, going through one important point, okay, is the decrement your counter, okay? So we can take a look. It's the decrement your counter here, okay? And if your counter, I don't know why you decrement it and it reach 0, then it will say that, okay, this guy needs to be rescheduled. This guy needs to be rescheduled. So this is the high-level point of view. And when you need to reschedule, it will eventually, the kernel will bring you to calling the schedule functions. So we have three main routes. One is the time interrupt. The timer interrupt say that, okay, please go to schedule. Or you call for I/O, you call for a keyboard, call for CD-ROM for servers, go to schedule. Or even because of this reschedule flag get turned on, you will go to the reschedule. And whenever you get reschedule, let's say the process N process get rescheduled, go through the timer interrupt, know that I have to forget about the CPU, I use up my quantum, then the switch to will switch to any one of the process that was previously get kicked out of the scheduler loop. Okay, and here is the moment that they stop. And in a kernel code, I can look for it. It's here. It's here, the switch to statement. Okay, and that's why after this switch to statement, previously is process N or process I, and suddenly become process J after this line. So after this process line is process J. Okay, it will maybe go to need reschedule back. So where is the go to need reschedule back? Copy, paste. Go back to the head of the scheduler. So why is that? Because maybe it's find that, oh, this guy is a good to schedule, but suddenly find that, oh, this guy is not very good, I don't know why. Then it will go back to the scheduler and choose another guy. And this is the control of the scheduler. This is something that you don't need to really remember it, but just tell you the real stuff that going on within the kernel. You switch to another process, and previously you are actually still in the scheduler. Okay? So after the break, we'll talk about assignment 1, how to do it, how to approach assignment 1. And after the break, we'll also let Helen to tell you how to install it. Install a head is not very difficult. Okay? The only difficult part is the kernel hacking. Okay? So let's break for 5 minutes. If you have any problem, you can ask me. Hello. If you're interested, actually there is 2 more scheduler warm up today. So the kernel version 2.6 up to 2.6.22 is using what we call a big-O-1 scheduler. It's just memory to trade for time. Okay, just a pre-compute everything, put it in an array, okay, and then immediately try to do a big-O-N selection process, okay, to look for the new process. And there is a guy called completely fair scheduler, which is working up to date, okay, because this is a very old notes. I do it several years ago, okay. So I also tell people to hack this 2 scheduler. They really want to kill me, okay, because these 2 guys are very hard to hack, really very hard to hack. They go through 2 different design principles. Okay, so in that assignment, they have to hack the 2 big-O-N, big-O-1, and CFS. Okay, in one assignment, and you guys only the big-O-N. Okay, because I don't have a very much time to prepare for this 2. Okay, very hard to hack. So I don't plan to ask you to hack it. If you're interested, you can ask me for this set of notes. Okay, let's talk about the virtual runtime in a CFS design, so and so forth. This is more latest version. And in our assignment 1, we don't hack the current 2 stuff. Okay, we only hack big-O-N. And the principle is very easy. I want you to set up 3 system call, which to tell the system that I want to start the unfair scheduling. And the unfair scheduling is so simple that we only focus on 2 processes. You specify their IDs, okay, and you will start to focus on them. Okay, so this is a design principle, and the thing is like this. Let's say that the first principle is I love to make up some funny names. It's called freeze the old guy. Okay, so you first of all get 2 PIDs. You decide who is the old guy. So we basically will only put CPU intensive job, so you can measure the CPU consumption. Then you will know which is the old guy, which is the young guy. Then when you find that there is an old guy there when I register, you freeze it by not scheduling that guy. Okay, not scheduling. Very easy, right? How to do the non-scheduling? of that guy, okay, think of it by changing the schedule function. Now remember, you are changing the schedule function now. So, you know what I want to say, okay? You are changing the scheduler. And what happens if you have a segmentation, I mean not segmentation, but null pointer dereferencing problem in the scheduler? This is no kernel ops now. It is kernel panic, okay? And the worst case, this is already the worst case of this program, this assignment, okay? So make sure that you have backup the old image. Helen will tell you how to back up the old image so that whenever you find that your new image always get a problem, you can still have old image to rescue you, okay? And so you stop scheduling that guy. Let's say I submit the call here. So for the coming 8 CPU time will all belong to the process B. I mean, compared to these two guys. Of course, in the system you have a different guys executing together, so you don't change other processes, only monitor these two guys and continue to schedule until their CPU consumption they get the same value, okay? And then you can release them, okay? Stop monitoring it again. You can overshoot, no problem. You can overshoot a bit. Let's say that you get lost control, okay? You cannot precisely having a 12, but it has become 13. So okay, you can overshoot. But don't overshoot, let's say, 100 to 12. Yeah, that means that you don't know how to hack. Okay? So then, let's go on. I provide you some good and bad hints. I don't tell you which hint is bad, which hint is good. Okay? Yeah, you think about it. You may try to hack the selection loop. Right? We have a loop to select which process to run. Or you change the goodness function. Yeah, tell the scheduler that who is the good process. Or you change the recharge loop. Right? The recharge loop is give the quantum to the process. Okay? So, which is the better approach? I don't tell you. Okay? Just let you to do some reboots. Okay? Yeah, this is kernel hacking, right? Like it's a lot of reports. Part 1. Part 2. Part 2, what is part 2? Part 2 is more interesting. How many of you didn't take a look at this animation? Yeah, you should all see this animation. So the part 2 is not to freeze the old guy, but share fewer resource to the old guy. Okay? So the illustration is similar. Well, these are some hints later on. We'll come back. We call it static scheduling ratio. So the ratio won't change until the two old guy and young guy get the same CPU resource. Okay. Then let's say again there is a guy executing earlier, gets accumulated 16 CPU time, and the process speed is 4. Then what should you do? When you submit, let's say the ratio is 2 to 1. The ratio is 2 to 1. Then you will start giving fewer resources. Now remember, it's to give fewer resources to the old guy. You can try giving more resources to the young guy. Yeah, you can try. Okay, maybe you need to reboot for some time. Okay, yeah, you can imagine. Hey, what happened if I put down 100 to 1 and you give more resources to the young guy? It will become very interesting. Yeah, it will become very interesting. Your system is suddenly frozen. Then move. Frozen and move. Understand what I mean? Because you give too much quantum to one process and your entire system just become crazy. Okay, very interesting. I see some people a previous year, because this I don't think you don't believe in it. Okay, so first of all, I designed this assignment, and can you guess what is the year that I designed the assignment? 2001. I designed the assignment is 2001. Okay, so I see many people doing this, okay? And the first time I designed the assignment is even more interesting. I don't fire 2 loops. I fire 2 movies. Okay? One movie start first, one movie start and later. Then I want you guys to sing the 2 movies playback. Just the same, right? Just the same, but from that time, okay, I choose a cartoon, okay? That year, student hates that cartoon so much. Okay. Okay, start singing. Okay, listen. The same. Okay. Hate the song, hate the movie. Okay. Yeah, so that's why I don't choose movie anymore. Okay, and this is the schedule less for the old guy, but schedule more to the young guy in this ratio, 2 to 1, 2 to 1, 2 to 1. Okay, so you can see my illustration. This is not, let's wait for a moment. You can see the 2 to 1 ratio very clear, very stand out. Now it's stop. Okay, so we start with close to 1-1-1-1 schedule because this is normal behavior for every system. Then we change its behavior, then run top again. You will see close to, then later we will see a very clear value. Now this is the point, 37 to 33, really a 2 to 1 ratio. Okay, very beautiful. Okay, some years before I see people really beautiful numbers. It even don't change. Yeah, you see some. I change it for a moment, right? That guy just frozen there, just like frozen the top. Right? I don't know whether it's this guy. Oh, you type top. Okay, I frozen it. Okay, it's just like frozen there. Very interesting. Okay, I know that guy is now in Octopus working, quite good. Okay. And we won't input a range number because if I input big number, the top will return me not so exact numbers. Okay, so we will only test up to 1 to 10. You're open to any numbers, but during my test, I only go to top ratio is 1 to 10. Okay, and I always start with 1 to something. Okay, and it's also integer, so you can try in your cases 1 to 2 to 3 to 4 to 5 up to 10. Okay, if this all behave normally, okay, that's okay. Now, what is our reminder? The reminder, first of all, please set the CPU to 1. If you have 2 CPU, the fluctuation will get worse. You are still doing the same thing, no problem, because you are controlling the resource. But because you have 2 CPU, okay, so you will get some not so steady readings. And second of all, you will be aware that I will suddenly press Ctrl+C over the process. Okay, press Ctrl+C to kill the process. If you're doing some wrong implementation, you'll immediately get kernel ops or kernel panic. Yeah, because you know what will happen, right? Ctrl+C, then you lost some control. Okay, and remember, don't put print k inside the scheduler. Okay, for 2 reasons. First, let's say you can call print k. And do you know what is the frequency that the scheduler get invoked? Yeah, then you will see the message, all of your message. And second of all, print k is an interrupt call. Actually, it will call the interrupt to print something on the hardware. And inside the scheduler, calling interrupt call is forbidden. Okay, so I didn't try, okay, because I don't want to boot my system. Okay, according to some years before, people report to me that they call print k in the scheduler results in kernel panic. Their observation, I don't know now. Okay, so go back a little bit. So how to measure which 2 processes? Okay, the 2 processes, which of them is older, which of them is younger? There is a structure. Let's go to the structure here. I don't have this file. Okay, the sketch.h, maybe I type it here. Oh, it's already sketch.h, sorry. Struct, task, struct. Okay, so inside this structure, we can find one field. Okay, where are you? Wait for a moment. Here, this field. Okay, this field is of a structure called TMS. Its name is called times. So what is this structure? Very interesting. This structure, when I click on it, you can find its definition. Definition is it measures something in terms of clock ticks. So it's not real second, it's in terms of clock ticks. And the first guy is the user time that already spends from that process on the CPU. Second, system time, user time, system time. And how about these 2 guys? These 2 guys is if your process will do fork and after you call wait to collect dead bodies of your children, then this field will collect also the time that used by the child. Okay, so it's called child user time and child system time. In this assignment, we don't use this child, we'll use these two. Okay, your user time and system time. Okay, and this is the times field, and inside the task struct. And inside the task struct, remember, you have to find a process out. How can you locate a process? Now you may have to write down because I missed it in the specification. How to look up a process, huh? In the scheduler, you can already find it. Okay? So, by looking at it, what do you know about this call? The return value is a task struct. You give a PID and give a task struct. So I don't think that you will guess another thing, right? It gives you the structure by your PID. Of course, you can write your own way, okay? You know that the 1Q, okay? You do a for each loop, or for each loop, list for each loop, okay? And you loop it by yourself. It doesn't matter, okay? But there is a call already implemented, okay? So there's the call that inside kernel, you have a PID. You want to find out whether the structure can be found, as well as you want to find that structure, going to take a look at the times, okay? Then you need this call. All right?